welcome everyone to the American Physical Society's topical group on the physics of climate seminar series. For those who have not been here before, this is a roughly monthly seminar series. Our target audiences are graduate students as well as postdoc and faculty who are curious about climate as a subject in physics. Of course, we welcome anyone to attend. I see we have a fairly wide variety of people. Just some mechanics before we get started. I encourage people to drop questions into the chat. We will, of course, have a oral question answer session at the end, or I can also ask them from the chat. I will hold off on asking questions, Laure, if there's something in the, turn it around. If there's something in the chat that's like clearly a necessary point of clarification, some term that people need, oceanographers know that physicists don't. I'll put that in the chat and I'll try to ask Laure at the earliest available opportunity. Otherwise, we can elevate them to questions at the end, and people have the opportunity to answer them directly and orally. But please feel free with questions. That's the whole point here, is to encourage this community to learn something new. Without further ado, it's our pleasure to introduce Laure Zanna, who's a professor of mathematics and atmosphere and ocean sciences at New York University, at the Courant Institute at New York University. Laure got her PhD in climate dynamics at Harvard. She then went on to Oxford University, where she was for many years before finally arriving at the Courant Institute. Among many awards, she's a recipient of the American Meteorological Society's Pufnapf Award for sort of creative work in the ocean sciences. She works in a rather wide variety of topics in ocean sciences and physical oceanography, including applications of machine learning techniques, physics-aware machine learning techniques, ocean dynamics, and their impact on climate, transport, and so forth. So without further ado, I will let Laure take it away.
Great. Thank you very much for the intro and for the invitation. Great to be here, I guess, virtually. So those talks are always super exciting because we know we're going to have people from everywhere, right? Basically, different institutions, different countries, different backgrounds. And it's also very daunting. Because you need to be able to actually speak a language that many people need to speak. And so I'm going to try to avoid jargon. It's always unpredictable. So as Albion mentioned, I'm very happy if there is a term that you don't understand that needs some clarification that is important, then feel free to do so. So my title was quite broad when Pedram, asked me to give a talk, and I really was, thinking about this idea of multiscale in the climate system. I think this resonates with, many physicists, especially on the fluid dynamics aspect of things, right? So we have a range of scales, both spatial and temporal, that interact with one another. And that's really what the climate system is, right? So we have interaction across a wide range of scales, from millimeters to thousands of kilometers scale. But we also have interaction between different medium, atmosphere, ocean, ice, and so on and so forth. So today, what I'm going to focus on is one piece, of the multi-scale physics in the climate system related to the ocean, because I am, I guess, in quote, a physical oceanographer. So I work mostly on the dynamics of the oceans and their interaction in climate. And I'm gonna, try to illustrate this idea of multiscale by focusing on one specific process. Those are called mesoscale eddies. They're, scale of 10 to 100 kilometers roughly in the ocean, and they're pretty important for transport. So I'm going to give you a lot of background at the beginning. There are going to be some movies and a few equations, try to describe what we're talking about. And then I'll talk a little bit about how we try to represent those multi-scale interactions in climate simulations. And also, can we learn anything new in terms of physics? I still believe this is one of the open challenges, both in climate, but also in fluid dynamics in general, this idea of multi-scale interaction, how things interact with one another. And I think this is, something where all the physicists' inputs are welcome. It's been, decades of work on this area, and still a lot of work to be done. So as always, when I'm going to talk about some of the results, I'm here talking, but I get no credit. Most of it is going to be with input from past and current students and postdocs, both at NYU and Oxford, and also many external collaborators. So I've been very lucky to work with a lot of people that come from different backgrounds. So let me repeat a little bit with some movies, because nothing better than some movies when we talk about multi-scale interaction. So I'm going to talk about this idea of multi-scale in the ocean, as I mentioned, and talk about those mesoscale eddies that I briefly defined, both in the climate system and in numerical simulations. And so here, just to give you an idea, those are very idealized simulations that tries to solve one piece of our problem. It's kind of the type of equations that are the bread and butter of geophysical fluid dynamicists. Basically boiled down equation of the fluid dynamics, on a rotating planet. And what you can see here are kind of filaments and jets, and those kind of vortices over here that, as I mentioned, in the ocean have scale of 10 to 100 kilometers and can derive their scale from instabilities of the jets and the currents in the ocean, and really can transport properties and mix back with the flow itself. Then I'm going to talk about how to solve the closure problem. So I'm going to define what the closure problem is, which is if I have a climate simulation that has a resolution that is much coarser than the simulation I'm showing you here. So basically, I don't have enough resolution to actually see those vortices grow. I don't have the right generative mechanism to actually make them exist. That means I'm going to miss part of this multi-scale interaction where those vortices are interacting with the jets. And that, again, has pretty big implication when we try to actually make simulations of climate, because we're missing one part of the physics. And that will influence how temperature is being transported, how different tracers are being steered, and so on and so forth. So how do we solve that problem? Again, it's been a long-standing problem, again, both in climate and in fluids in general. And I'm going to talk a little bit about how people have been doing it for a long time, and how now with new tools from data and machine learning, can we do something in between, and can we learn anything new? So that would be the idea. And now I'll give a few concluding remarks. So I'm going to start a little bit because, at the end of the day, those talks are a little bit personal, right? I come with my own idea of what I believe is a big challenge and something that many people have been working on for a while. And one of the big reasons that I work on, ocean dynamics is, the ocean basically covers 70%, of the surface of the planet. It's a pretty big, sink of heat. So here, what I'm showing, so it's a movie, you can see the clock up here. It's a reconstruction of ocean warming. So we're integrating the temperature top to bottom in the ocean and running that. So it's a reconstruction, so it's observation and a little bit of models and some theory. And so where it gets very yellow and red, it basically means that there's a lot of warming that is accumulated. And you can see that it gets, basically warmer and warmer as we go from the past into the present. So the ocean has been basically taking up most of the excess energy that we have in the climate system. We put greenhouse gases in the atmosphere, right? So we're warming the atmosphere. Most of that excess heat and energy is being absorbed by the ocean. Okay, and that's why the ocean is such an important piece, of the climate system, is because it actually takes up a lot of heat, also takes up a lot of carbon. And the way it does that is there are some regions, as you can see, that are accumulating more heat than other, or taking up more heat than other. North Atlantic is one, and here the Southern Ocean down here is another. So those are a little bit, if you want, the lungs of the ocean, absorbing tracers that come from the atmosphere into the ocean. And all of that is, of course, driven by physics, right? So basically how the ocean will absorb and then transport that heat around is completely determined by partial differential equations that are coupled with one another. And so here's an example. So I'm showing you on top the movie up here again of this reconstruction of ocean warming. And if I look at trying to understand what the ocean, dynamics look like. So I would write those PDEs over here. So on top is the Newton's law for us, right? So that's F equal ma. And so our acceleration has two components, one that is purely local. So U is going to be momentum. And I'm going to look at the rate of change of momentum plus a non-linear term here. So this is called the advection. So this two term here is basically the total acceleration of a fluid parcel. So that will be our A, that would be our acceleration. And then we have a bunch of other forces. One is the pressure gradient term, right? So basically, again, we're talking about the fluids. So pressure gradient will actually drive currents in the ocean. Gravity, obviously, right? That's one that all physicists know, no different, right? So that's an important one. Viscosity or dissipation. And if we were thinking about the ocean, then the forcing of momentum at the surface of the ocean will be the wind blowing, and that can generate currents. And now there's this extra term here that you can see, omega cross u, and that's because, again, we're on a rotating planet, so that would be the Coriolis acceleration. So you can see we have a pretty complex F equal ma when it comes to ocean dynamics, right? And you will have something similar for the atmosphere. So solving those kind of partial differential equation is not a piece of cake, and it can describe both this large scale transport that I'm showing up here, but also those kind of more turbulent flow field, which is really what the ocean looks like in general. And so the same equations are actually explaining both of those phenomena, large-scale transport of warming, but also a lot of the ocean turbulence. So the momentum equation is one equation, right? But that's not it. That's not the only equation that we have. We also have an equation for density. So rho is density. And in the ocean, it's going to depend on temperature, salt, and pressure. So one little funny thing about the ocean is, so this is what we call an equation of state, so a relationship between our thermodynamics variable and pressure and density. We don't know what the equation of state for the ocean is. So what we do actually is usually we have an empirical relationship, which is a Taylor expansion. And we have a bunch of coefficients that we basically either derive empirically or using some measurements. So this relationship is actually not really known. And so this is already one big question, is what is the correct equation of state for the ocean. But nonetheless, we still have a conservation of mass basically over here. And then we have two thermodynamics equation, one for temperature. So the rate of change of temperature plus, again, this kind of nonlinear transport is going to be equal to some dissipation, or some basically diffusion of heat, and then some forcing. So again, some heat flux. And you're going to have the same for the salinity. So pretty complicated sets of nonlinear partial differential equations that we need to solve if we want to explain both, both pieces of the ocean. So those equations, right? So again, we can't quite solve them, but we can, put them in a computer, and I'll come back to it in a bit. But if I were looking at what ocean currents look like, again, driven by those equations in a model, so this is what we would see. So the color bar is over here on the right. So we basically go from centimeter scale, roughly, in terms of our currents. And what you can see is that some places of the oceans have, stronger currents than the other. So here's the Gulf Stream, right, detaching from the coast of North America, the Kuroshio off the coast of Japan. Southern Ocean has also very strong currents, but so are the equators. But other places have also, kind of weaker currents. So wide, range of behavior in terms of what the ocean looks like, in terms of currents and so on and so forth. Now, if we were looking at kinetic energy in the ocean, right? So I showed you currents, so they can be pretty strong in some region of the ocean. Now, again, another quantity that we like to measure, both oceanographers and I guess physicists, is kinetic energy, right? So that tells us something about how much kinetic energy is available. So if I have the currents, I can actually calculate how much kinetic energy we have. And again, it's in a simulation. And so you can see that obviously some of the places where you have strong currents will be some of the places where you have very strong kinetic energy. So again, not completely uniform, but it tells you that some parts of the oceans are more energetic than the other. So, and again, we're kind of slowly getting towards this kind of scale interaction. Large scale currents, now kinetic energy that have much smaller features embedded in them. So we already start seeing the emergence of smaller scale derived in places where you have large scale gradients and very strong flow. So now let's look at observations. So those are indirect observations of sea surface heights. So basically you have a satellite that, bouncing a radar beam to the surface of the ocean, coming back up, and we can calculate the time it takes, for the signal to go back up. And from that, if we have a reference surface, we can calculate the sea surface height from this reference state. And so what it is basically all the red and blue blobs that you see here are the ups and downs of the surface of the ocean. So first, it's not, right? So those are anomalies from a reference state. And what you can see is a lot of small scales, right? So lots of features, again, so now, the Atlantic is on this side and the Pacific is on this side. So a bit different, but doesn't matter, right? It's our Earth flattened. So the same places where we had our very strong current, the Gulf Stream over here, Kuroshio over here, you can see those kind of small features emerging. Okay, so those kind of, again, those scales that have roughly 10 to 100 kilometers are basically, coinciding where we have those turbulent jets. So basically completely derived to first order from instabilities of the strong current. And the Southern Ocean is the same. A lot of those blobs popping up in those kind of regions where we have very strong currents and where those eddies, which here we're defining as a deviation from a time, are deriving their energy from. So let me pause for a second, just in case there are some questions so far, but so far so good? Okay, great. So showed you a few things, right? Both from models and observations. Complicated nonlinear partial differential equations. They can describe both the large scale flow, right? So large scale structures, but also they are the same equation that will give us rise to those instabilities that we see, the currents. Those are the same equations, right? We really are solving the full range of scale with the same equations. But also what we see is that there is some, collocation in quotes of the places where the instabilities are large and where, the currents are large or where the gradients are quite large. So again, it's all visual, obviously, but just to give you a feel. So now if we're thinking, again, we talked about momentum, we talk about, temperature and salinity. I can make the same stories out of it. Now, if we were continuing along the line of energetics, so most of those eddies that I showed you before with those scales of, 10 to 100 kilometers that we got from altimetry data are actually composing the bulk of the kinetic energy in the ocean. So one way to show you that is here is a 10-year average of the eddy kinetic energy. So again, I'm defining an eddy as the deviation from a time mean here, okay? And so if we look at the eddy kinetic energy, all right, so the energy from those, features of 10 to 100 kilometers, you can see that most of the kinetic energy, again, is in the same places as before. Southern Ocean, Gulf Stream, core shear. If we were to calculate the ratio between the eddy kinetic energy and the full kinetic energy, what you can see is basically, few hundreds of magnitude larger. So most of the kinetic energy is actually contained in this eddy component. So the mesoscale are really basically, if you want, encompassing the bulk of the kinetic energy of the ocean. So they look small, they look, pretty turbulent. They might look like they do nothing, but actually they contain the bulk of the kinetic energy in the ocean. So just again, to give you an idea in terms of kind of physics stuff. So let's try to put that onto a scale, right? I showed you a bunch of movies with different scale. I'm going to show you one more in a second. So we have an axis of small scale towards large scale. So from small on the left to large on the right. So large scale will be things on the basin scale, roughly, right? So it's going to be thousands of kilometers. Mostly those currents are driven by the wind and the buoyancy, the stuff that we have on the right-hand side of the equations. And it can really define this kind of large-scale transport, where we saw a lot of kind of the large-scale currents. So this is going to be one scale that we're thinking about. The other type of scale that we've been, seeing in our little altimetry movie, and I've been talking about that contain the bulk of the kinetic energy, are those mesoscale eddies. 10 to 100 kilometers. Here's a snapshot of the Gulf Stream. You have those sharp, currents, and you have those kind of rings that, again, have those scales of about 100 kilometers or so. So now we're getting to smaller scale, but again, those scales are derived from the instability of the large scale flow. Then you can continue going down in scale. Submesoscale. So here that will be the mesoscale core that we have here, for example. And you can see the submesoscale are those smaller features that are around here, 1 to 10 kilometers. Their mechanism, they're basically the driving forces were different than the mesoscale, but just again to show you the range of scale that we have. And of course, we can go all the way down to dissipation. So same equation that we showed before really are encompassing the range of scale that we have in the ocean. So I'm going to pause for a second just to see if there's anything. And in the meantime, I'll.
There was one question about the prior slide. About the prior slide, someone asked, what's the total kinetic energy represented in the ratio plot? What's eddy kinetic energy 100 times greater than?
Sorry, you cut out for me.
It says, the question is, what is the total KE represented in the EKE over KE ratio plot? That is, what is the EKE 100 times greater than?
Oh, it's 100 times greater than the kinetic energy that is, so basically you can actually just multiply it, right?
Right. So I get, right. I guess it's the total velocity versus the eddy component that you're
correct,
squaring.
versus the eddy component. Correct. Yeah, that's correct. Indeed. And I should mention, and I'm going to talk about it in a second, most actually of the energy in the ocean is contained in the available potential energy. So if you want kind of the availability of potential energy to be there. So even though we do have a lot of kinetic energy, it's not the dominant part of energy in the system. So I'll come back to that in a second.
Yeah, this is also maybe a good question for now. Someone asked why the small features move westward.
All right. So that's a very good question. So I'm not going to talk about any of those things. So basically, there is, propagation. I know maybe Tiffany will talk about Rossby waves and westward propagation at some point. But yeah, I see you on the spot. Maybe. So that's another piece of the physics I'm not going to touch upon in terms of westward propagation on a rotating planet. Yeah. But definitely, the rotation and the fact that we're on a sphere are the dominant contributor to the propagation as a rough answer.
Thanks.
Yeah, great. Excellent. So again, wide range of scale, and again, it's amazing actually that people are picking up on other things that I haven't talked about, but all those things are described with the same equations that I showed you. And that's again, almost kind of the beauty of it, is you can describe so many different phenomena on so many different scales with the same equation, kind of really touched upon the complexity, of really the kind of problem. And here I'm only talking about the ocean, right? But again, the same challenge will be faced when we talk about the atmosphere. So back to this kind of idea of multiscale and also the different parts of energy. So as I said just before, the mesoscale are a major player in the energy cycle. So one, again, they form the bulk of the kinetic energy in the ocean. The second thing they do is they actually extract the energy from the mean state. Okay, and that's one important thing, is they exist because they can extract some energy from the mean state. And they extract it at a given scale that is called the deformation scale. And I'm going to come back to it in a bit. And what they do is they extract the energy from the potential energy that is available for them. All right, so there is a certain part of potential energy that they can extract, and they convert that into kinetic energy. I'm not going to, add more terms. I should have get rid of it, but there's a term for that instability. And really, it's this extraction of available potential energy. So the potential energy that is available for the energy to grow, they transform that into kinetic energy at a deformation scale that will depend on the rotation and how the ocean is stratified, meaning how the density is stacked up as a function of depth. And so that's an important scale, right? So that's an important physical scale that we understand quite well. So now why they're important, right? So you could say, well, I mean, why do I care, right? So the flow becomes unstable, those eddies shows up, but then, they just transform into some kinetic energy and nothing happens. But what happens actually quite often is that as they at that scale, right? So when they extract their energy into kinetic energy, they can actually backscatter. So they can basically grow if you want. So another way to think about it is they can merge together and impact the larger scale. So now it's not like they're gonna go and dissipate, go to the smaller scale and get smaller and smaller and everything will go away. They can actually backscatter and influence the large scale flow. So they extract the energy from the large scale state, they grow, and then they can go back and basically re-inject momentum, re-inject energy into the large scale flow. And so again, if we take a step back and think about the climate system, that means that the large scale transport of heat, carbon, oxygen, and so on and so forth can be strongly impacted by those mesoscale because they can extract a lot of energy and then backscatter it through an inverse energy cascade into the large scale flow. And so that's why they're so important, is they're not just going to disappear and move things away. They can actually go back into the large scale flow and influence the large scale climates. So here's another way to actually show exactly the same thing in terms of this idea of inverse energy cascade and backscatter. So let me try to play that movie. So very simple movie of a bunch of vortices. What we have here is you can see that the vortices are not disappearing, right? They're actually sticking together, and some of them are getting larger. Okay, so again, it's a very simple example, but just to show you an idea of those kind of vortices having scales that are larger and larger is what they've done. If they extracted energy from the mean state, grew, and then basically became larger. So simple way to show that in a very simple movie. Another way to see it in terms of kinetic energy. So it's an illustration here, to be clear, it's not the real deal. So we're gonna have kinetic energy in kind of log power of it versus wave number, also in a log plot. So everything is a log plot. On this side of the axis are the small scale. On this side of the axis is the large scale, okay? So we have a lot more energy at large scale than we have at small scale. But what's interesting, again, it's this kind of same idea. Some of the energy, right, that this is basically kind of being extracted from the available potential into the kinetic energy is gonna go back up as an energy cascade. And so the point is, if I were not to resolve those scale, those eddies, I would kind of cut my spectrum over here, and I would cut part of the energy sources that I have at large scale, because some of those sources are coming from scales that are not resolved. Okay, and that's why it's important, again, is the amount of energy that is contained at large scale will be lower if I were not resolving those eddies, because again, they can actually transfer energy upscale. Okay, so this drives me to climate models, right? So I told you all that stories. Eddies are important for transport. You know, they're unstable, they're turbulent, they interact with the large scale. So do we resolve them in models? Well, in some of them. So this is a climate simulation from colleagues at GFDL. This is a 1/10 of a degree climate simulation. So it tries to solve the fancy PDE I showed you before, but they're still pretty approximate. And it solved them on a grid that has a resolution of 10 kilometer by 10 kilometer. So 1.1 degree by 1.1 degree horizontally. And you can see basically all the features that I told you before, right? I have the jets, you know, I have the Gulf Stream here detaching from the North Atlantic, lots of those turbulent mesoscale eddies that are, you know, deriving, you know, their energy from, you know, from the gradients in the flow and interacting back with the jet itself. So that's, you know, kind of a beautiful movie, but also really something that tries to capture the mesoscale and their interaction with the large scale flow. Now, not all models are like this, right? So to be able to resolve eddies, you need to be able to resolve this thing that I call the deformation scale. And it's this ratio between stratification, so how the densities are basically stacked up as a function of depth, times, you know, the layer thickness that you're considering, divided by the Coriolis parameters, which is basically a measure of rotation, right? So it's basically stratification over rotation tells us when, you know, those eddies can exist and what their scale is and what do we need to actually solve it. And so this is a nice, you know, calculation from Byberg in a paper saying what will be the grid resolution required to actually resolve those mesoscale eddies in a climate simulation, right? In an ocean simulation. And so it's kind of unbelievable. The simulation I showed you right now, right, is about 1/10 of a degree. So it would be this kind of, you know, color over here. And you can see that in quite a few places you can resolve them. But then if you go to the Southern Ocean and the high latitude, actually even that superb simulation struggles to actually resolve mesoscale, or at least not in a region that we want. If you go near the shelves, all right, so along the coastlines, then we're not even close to it, right? Would need basically, you know, 1 to the 50th of a degree resolution to be able to solve those scales. And as I said, they're pretty critical, right? They draw their energy from the large scale fluid. They're actually important for tracer. They interact with the large scale. So, you know, even just that model that I showed you, even though it can resolve some of the eddies at some of the places, in many places it doesn't. And one of the simulation I showed you, it's really one of the state of the art in terms of resolution. The majority of our climate models are actually run at coarser resolution than that. And so here's another way to represent the same thing. So this is the 1/10 of a degree simulation that I just showed you around Antarctica. This is the same simulation, but run at 40 kilometer and here at 100 kilometer. And that's usually kind of the typical resolution of our climate models. So those features, those filaments, the turbulence, and, you know, and the uptake of heat and carbon, the melting of ice is quite different because we're missing those scales. So I'm looking at time and I just, I forgot I have 45 minutes, is that correct? Yeah, okay, I see people nodding. So I'm gonna skip that and just show you that if you look at those 3 simulations in a climate model, then we see exactly what I told you in words. So this is the kinetic energy as a function of wave number. The high resolution simulation here, 8 degree, right? So we have this kind of shape with a drop off here. So lots of energy over all scales. Now a resolution of a model at 30 kilometers. So now I'm only partially resolving some of the eddies. So first, the energy levels are dropped everywhere, right? At all wave number, not just with the small scale, but the large scale as well. So already kind of, an indicator, or if you want a symptom of the lack of mesoscale or not enough mesoscale. Now, if you run it at 100 kilometers, then, okay, this is way off, right? We're on the log scale. So this is a major drop at all wave number. So not resolving eddies really kind of basically damp the amount of energy that we have in the system quite drastically. And that has an impact also on the currents. So here I'm showing the velocity in the Kuroshio region, latitude, depth, and again, depth, latitude in those three simulations, and you can see that the jets structure are very different, right? So here at high resolution, the jets are stronger, they are deeper, right? They go down to 2 kilometer depth. Coarser resolution, they're much weaker, they're not as deep. So again, you can already think about the implication. So, okay, are we doomed, right? Is there nothing to do? And if there is, hopefully there is, what should we do? How can we represent the interaction between those small scale, those small eddies, and the large scale fluid? And so the way we think about it is by thinking about the parameterization or the closure problem. So if we were writing, in a very simple way, the truth continuous equation that we had before, but I condensed them to make our life easier, right? So I'm just taking the momentum. So the local rate of change of momentum plus advection equal forcing and dissipation. Those same equations should apply into a coarse resolution model as well, right? The same one I showed you before, but clearly we're missing something. It's not energetic enough. There's lots of errors in the currents. So I'm missing a term. I'm missing, in my F equal ma, I'm missing a kick when I'm at coarse resolution that comes from those mesoscale eddies. And so the way we can do it is we can say, well, in a perfect coarse resolution model, I should have an additional term here. Okay, so bar is for coarse resolution grid. So for my coarse resolution, I should have an additional term that in a perfect world should give me the same physics as the high resolution model. Okay, and that missing term is really the difference between the, if you want, the Coulson advection on the coarse resolution grid and the coarse advection. Okay, because the simulation will only solve those equations over here while I have no knowledge of the high resolution term. So we're really trying to stick on the right-hand side this term in a coarse resolution model to make it behave as a high resolution model without the cost of it and still by being on a coarse resolution grid. Okay, so this is really the crux, if you want, of the closure and the parameterization problem, is to find a relationship for that S that is missing in a coarse resolution model that will only depend on the coarse resolution variable, but that will do the same thing as those scales that we're not resolving. So we're trying to basically represent the effect of the mesoscale onto the large scale without knowing what the mesoscale are, because we can't resolve them. And that's what we're trying to learn in this kind of parameterization or closure problem. So that's really the game. And so I'm going to show you just a couple of examples just to illustrate what I'm talking about in the last 10 minutes that I have. So the way people have done it traditionally has been to say, well, okay, let's find this kind of closure term, this kind of subgrid term that is missing at coarse resolution, and that depends on the on-coarse resolution by considering, physical theory, which usually are just trying to think about what the mechanism is doing, or doing a little bit of, pen and paper and some simulation and saying, okay, can I come up with a mathematical form for what those terms are supposed to be doing? I'll take the simplest possible example, which is viscosity and dissipation, right? In my climate model, I will never resolve all the way down to the molecular scale to actually have truly molecular diffusion. But we know we have some dissipation of scale as we get to smaller and smaller scale. So mathematically, I could write it as the Laplacian of U, and that should behave as dissipation. And all I need to do is to figure out what the coefficient is. So I have the form, I have the mathematical form, and I know roughly that's what it's supposed to do. Now I need to figure out, what mu is, but you can do it empirically. So this is the simplest form, right? I'm exaggerating a little bit, but there are a lot of theories that relies on those bulk formula ideas. Try to come up with a mathematical representation that is idealized of the process that is missing. So that would be one extreme. The other extreme is you could say, well, I know nothing about nothing. Let's go and learn it from data. Let's take the high resolution, extract the missing term, and then learn it. Okay, neural network, anything you want, a statistical model, you know nothing about nothing. You're just trying to find a high dimensional, relationship that will characterize what you want. So, people like to kind of, make them fight against one another. One is completely physics driven. The other one is data driven. So there is no knowledge and, it's physics free. I would not necessarily agree with that characterization, but, you could go at it with just looking at the data. Or you can do things a little bit in between, right? You can start with the formula and then try to fit the parameter from data, right? So that could be something in between. Or you can take data-driven algorithm and constrain them physically, because we do know some of the structure of the physics. They can be conservative, for example, in terms of momentum. So you could bake that in. So, the scale is not really left or right. There's a full spectrum, like the same way we have spectrums of scales. Now, of course, each one of those, left or right has their own issues, right? And so you could argue that optimizing parameterizations don't necessarily reveal new physics because you've made an assumption about it. So you might be missing something. The other problem with the, neural network approach is try to interpret, a function with thousands of parameters, right? It's going to be pretty difficult because it's high dimensional. So is there something in between? And so I'll show you an example of something that we think could be a viable option, right? So trying to actually learn physics from data for this closure problem. And of course, there's a big question mark, right? We still, the jury's still out if it works and if we're truly learning new physics. But for some of the pieces of the problem, we are learning something about how scale interacts with one another. And the pros of it, of course, is you get mathematical equations, so it's fun, you can do something with it. So here's an example of something we've done a few years ago, where we diagnose this missing term, right, that comes from the eddies, from a high resolution simulation, and we ask an algorithm to learn it. Now, the algorithm is a sparse regression algorithm. So we give it data, and we also give it a library of function that is built from the data that will contain, the velocities, the gradients of velocity, gradients of temperature. So you really give it a dictionary of function, and you ask the algorithm to basically iteratively go and select the function based on the library that you give it that will best match the missing forcing that you diagnose from a high resolution model to replace, what's missing in a coarse resolution one. So pure, if you want, fancy regression of a machine learning algorithm that goes and prune the library of function that you've done. Pedram did something similar, for a different problem, but that's really kind of the game. Let's try to learn an equation from data and see what we come up with. So in this case, we're learning the missing part from the mesoscale onto the large scale only for the momentum equation. We've done it for temperature. I'm not going to talk about it. But the beauty of it is you still end up with something that actually makes sense, which, that's one good part of it. We ended up with a symmetric tensor that actually depends on the stretching and shearing and vorticity of the fluids. And we were able to relate how this tensor actually affect the transport on larger scale. So really trying to understand this multi-scale interaction of momentum and energy in the fluid. Now, of course, you could say, well, all those terms are known, so it's not new physics. So that's not what I mean by new physics. For me, the way I think about new physics is how the different parts of energy and momentum and tracer will interact with one another, and how do they impact the large-scale fluids. And so that's what we were able to learn by taking this, expression and putting it on the right-hand side of a coarse resolution model. And it does better, right? So basically, that's a coarse resolution model with no parameterization. That's the coarse resolution model with our parameterization. So that's the velocity, and that's the standard deviation, and that's the truth. So you can see that it basically gives you something that looks like the high resolution one. But again, the beauty of it is now we can go and diagnose, how the different terms have interacted with one another and teach us something about what we were missing to begin with. So I'll show you another example, still of, this idea of learning a mathematical expression or trying to learn new physics from data. So before that, I had to build a library of function. And so you could say, well, Laure, you cheated. You give the answer. So of course, it's going to find what you wanted. So one other idea is let's not give it the answer. So we can use a different algorithm from genetic programming that is a purely symbolic type idea, where you start, with basically a random seed, and then the algorithm will actually build a set of multiplication, addition, and so on and so forth of your function, of your data, of your function. Okay, so now you're not basically feeding it the answer. The problem is those algorithms know nothing about spatial things. So we had to actually hack it to introduce spatial derivatives, so we can actually take derivatives and and introduce some what I call human intervention. And so my colleague Andrew Ross would call it human in the loop intervention, meaning that you don't want the algorithm to do something stupid, like adding velocity and temperature together, not the same units, right? So you have to be a bit careful because algorithms don't know things. But the beauty of this is that you can go as deep as you want. It's not going to be limited by what you give it, because it's going to symbolically find something that it wants. So some results, just roughly, this is the high resolution simulation, low resolution. This is a baseline of a low resolution model with a physics-based parameterization. That's one when we learn a neural network, and one where we have our equation discovered. So by eye, they all kind of look the same, right? They all do well. If I look at a power spectrum as a function of wave number, the coarse resolution is the gray line, the truth is the black line, and you can see that pretty much all of them do roughly well. Some are doing better than others, but I would not squabble by saying one is better than the other. But actually the fact that they do something relatively similar is actually encouraging, because it tells us that there is something being captured by the data that is useful. Now, what's more mind-blowing is now still the same PDE, but let's say I change beta, which is the change of the Coriolis parameter with y, with latitude. So same physics, technically, right? Same equations, but the physics is a bit different now. I have jets, okay? So, but I've learned in the configuration that I had no jets. But technically, if I learn real physics, that should still work when I put my parameterization on the right-hand side. So this is the jet at high resolution, low resolution. This is a physics-based parameterization. Compared to the low resolution, I see no difference, in all honesty. And even when we calculate as a metric, we see no difference. If you put a neural network, this is not good at all. So it goes crazy. I actually inject too much energy at large scale and almost look like the eddy configuration. It destroys the jet entirely. But our equation discovered one actually does pretty well compared to the high res. So this kind of idea of learning only a few terms rather than learning a million high dimensional function seems to actually generalize better. Now that comes to it, right? There's some reason for it, and I can come back later. But let me just conclude, so I stay on time, because I don't like to be late. So I want to say a few things just as a kind of a remark. So I give you some example here, right? So scale interactions in the climate system are really ubiquitous. We have nonlinear equations, as I said, a multitude of phenomena, both in the ocean atmosphere and pretty much any component of the climate system you look at. And so that makes it super challenging, but also really exciting. Again, right, you have those very complicated PDEs that we can't solve by hand, but looking at different pieces of the problem has been helpful. But yet, every time I look at one piece of the problem, I'm truncating this multi-scale interaction. So trying to take a step back and rethinking the way we see this exchange of momentum, energy, and so on, potentially from data could be something interesting, right? With the knowledge of physicists always. So it's kind of this interaction between PDE, data, physics, and of course, numerical modeling. And so I believe that there is a lot, I think there's a lot to be done at the interface between, those different disciplines with a strong, understanding of physical mechanisms and PDEs, with joy of working with data and numerical models. I think, the many doors are opening, and I think it's a really exciting time to really kind of bridge this gap, across the kind of physics driven all the way to data driven. I don't see them as one versus the other. I really see them as coming together in a very complementary way. So I'll leave it at that, and I'm happy to take questions, clarifications, comments, and so on. Thanks.
Thank you, Laura. That was amazing. I guess I'll ask for questions. Maybe the best way to do it is for people can use the raise hand app, and then I can call on people in turn. You can also drop questions into the chat that I can bring up. I got a question from Joe Podlowski. I think you can unmute and ask. Hello? Let me just check. Do I have to? Oh, allow to talk. Let me. Sorry, you think I'd have this by now. There we go. Sorry. Okay, now you can ask.
Okay, thank you very much, Laura, for that.
Hi, Joe.
Hi. The question that always comes to my mind in these oceanic cases where the deformation radius is so much smaller than the scale of the general circulation, although it's not that much smaller than the scale of the strong currents, is I suspect that the eddy's interaction with the flow will be concentrated in the region of the strong currents and not so effective in the large regions of the open ocean that are driven externally by buoyancy and wind stress. Does the learning process, the machine learning process, does it really point that out? And distinguish the non-homogeneity of the eddy mean flow interaction?
Yeah, thanks, Joe. That's a great question. So one side that I skip actually is exactly this idea of, eddies interacting with jets, right? So you get basically kind of, convergence of momentum, and you can accelerate the jet in those regions. And in places where you don't have strong currents, where you have this kind of more, I don't want to call it isotropic, but more, as you said, homogeneous type turbulence with no interaction with the large scale fluid, then yeah, the physics is quite different. So with the neural network type ideas, no, actually it doesn't do well at all in capturing those differences, unless you start forcing some additional constraints. With the equation discovered piece, actually it does better because it's forced to only learn a few terms with very few parameters. So we were able to actually show that it can really distinguish between those two pieces. And only in that specific case. And that's why, one has to be very careful with those learning algorithms to actually know something about the physics. So you don't end up overfitting and end up with solutions that have nothing to do with physics, but are just, a regression problem.
Thank you.
Any other questions? Well, I wait to saw we do have one from Elise Roski. Go for it.
Hi.
Hi.
Thanks. So I'd always thought of energy being dissipated from the large scales out to the smaller scales. So I thought it was really interesting to see the reverse process. And I guess I just wanted to clarify one term, the entropy term. So is that the process of energy being dissipated from large to small scales, or what was that term exactly?
Yeah, okay, thanks. So that's two great points. So one of them, yes, this is what's special about, about GFD, is that we do have an inverse energy cascade because we're in a stratified fluids, as opposed to 3D turbulence that, many people are familiar with, where energy is cascading only downscale with no inverse energy. So yeah, so that's definitely a great point. Entropy, yeah, I kind of skipped over it. So entropy, it's kind of another way to think about, I would say, potential density. So it's related to kinetic energy in the fluids, and it does relate to dissipation. So it's, one way to think about it, and it's vorticity squared, basically.
All right, thank you.
Sure, and thanks for the questions.
We've got some questions from the panelists. I'll just start with Pedram and then Chenya.
Thanks a lot, Laura, for the fantastic talk. So I have two questions. One is, given the purpose of these seminars, what kind of advice you could give students, postdocs who their background and expertise might not be in climate science, but they might be interested in contributing to this field? And my other question is, so for machine learning and also for validating these models that are developed, we need data from models and from observations. So you are leading a number of major projects. I'm wondering if you can say a few words about the role of data and where we get these data.
Yeah, great questions, both of them. So, I mean, in terms of advice, right? So I actually do think physicists are I was in a physics department for a decade. So all my students came from physics with absolutely no knowledge, right, of climate as graduate students, but all of them had very strong background, right, in math and physics, right? So basically, anything related to classical mechanics, strong, math background, and that's really, what we're looking for, right? And nowadays also most students learn something about numerics, which is also pretty important for us. I'll come back to your question about data in a second. So I think that's really kind of the baseline. Then usually there is a book that I like to give physicists to begin with when they start. So first, of course, I always say something in fluid mechanics is helpful, even if it's a simple one. All right. So if they can take a class in fluid mechanics, whether it's from physics, engineering, and so on, I think it's a pretty good, I think it's a pretty good start, because again, it's really PDs in a twist, right? So I always feel like it's a simple start. And then when they have that kind of background of a little bit of fluids, then I give them the very old book from Cushman-Rosen, super small. It's only a few chapters, and you can read that in a few weeks. There's a lot of jargon, but it's fast and it's really good physical intuition. And it starts from the very basic stuff. Now, of course, it's out of print. So if you want to buy it, it costs like $2,000. So don't, because there are actually a lot of version, online available in a proper way that one can get. And so a lot of students and postdocs that came outside of it thought it was actually a good one. So there are two of them, right? The new Cushman-Rosen is really big. It's amazing, but I would not suggest starting with that. But there is a very, very small one, the very first edition. So a small start. Then your second question about data. Yeah, data is hard, right? So I cheated here. I told you about things where I could generate a lot of data because, I can either run the simulation or somebody else did it for me and very kindly gave us the data. So for other projects, we're stuck with not enough data when we don't have the PDs for it. And many parts of the climate system, we don't have the right PDs for it, right? We don't know what they are. And there that's an issue. So how to combine the little observations that we have that are in direct measurements and noisy and scarce with some simulation, that's definitely one of the challenges ahead of us. So, I always feel like we can separate the problem a little bit, somewhere we have simulated data and try to teach us something, and then slowly build up the tools and the knowledge, to expand upon it. And of course, you are the experts on all of those points. So we're definitely following your lead on that one.
Thanks. I put what I believe is the correct spelling of Cushman-Rosen in the chat for anyone who wants to see that. And I think Jing had a question.
Yeah, thank you for a really inspiring talk and also just advice for students and postdocs. So I guess I have more technical questions about the sparse regression you mentioned for learning the ocean subgrid parameterization. So I guess in this case, the data is numerics, right? So if now, right, if somebody want to extend this to learning models from observations, there could be noises from the observed from the data. So would this, I guess, sparse regression algorithm be sensitive potentially to noise? Because I guess you have function library, but there could be infinite number of combination of functions that can describe noisy data.
Yeah.
Wondering what you think about this.
Yeah, that's a wonderful question. So there are quite a few of those algorithms of sparse regressions out there. Some are more or less sensitive to noisy data, depending on how they optimize. The one that I showed you actually is a lot less sensitive to noisy data than others that are more widely used, actually. So the one we're using is a Bayesian sparse regression, so a bit more robust to noisy data. But it's a big question, actually, and that's also one of the reasons we moved away from sparse regression. One is because the data can be noisy, but even with numerical data, I'm taking derivatives, right, of like small scale features. That's not good, right? That makes things even smaller and smaller. And so the higher the order of derivative, the smaller and smaller the scales that you're looking at. And so even though your data is not noisy, but you are introducing noise by taking derivatives of them. And so that's one of the danger. So there's a lot of work on the algorithm themselves to try to make them more robust to noise, but that's something that one has to be very, very careful about. And that's why we tried multiple methods also to see if we were getting the same answers. Because that's not good, as you said, right? You can have multiple answers. And a final point, which is, and I should have said it and I didn't, but at the end of the day, the algorithm learns something that looks like the data. It might have nothing to do with the real physics, because you're just fitting something, right? And I think one has to be very careful, and that's why we're doing the thinking after the fact. But it's very important to do the thinking after the fact, because maybe it gives you something that is uninterpretable, and just find a good correlation with no good physics in it. And that's why, again, physics is good. Physics is good, right? That's why we want to keep the physics intuition and building the right theory for it.
So we have another question from the Q&A from John Line, if I'm pronouncing it right. It says, can you remind me how TKE is dissipated at larger scales in quasi-2D turbulence? At the Kolmogorov microscopic scales, its TK is smeared into heat. What is the energy dissipation mechanism at large scales?
Yeah, so we've got basically a lot of what's happening in quasi-2D turbulence is that what the mechanism that we're thinking about is what we call barotropization. So we make basically the column more barotropic. We extract energy from the available potential energy, which is the density as a function of depth being stacked up, and then we barotropize the flow. So we have flow that is more kind of uniform as a function of depth, and bottom drag is going to be one of the big, big way to dissipate some of that barotropic energy.
Before we go, maybe just one question. The parameterization you looked at looked rather local in time, but I could imagine if the large scale excites the smaller scale, then it travels upscale, there should be some time delay or memory. Is that something that people worry about? Is it a big deal? It's a
huge worry. Yes. This is one of our favorite topics. How do you include memory? I mean, Pedram has worked on some of that as well. So with some of the algorithm we used, for the equation discovery, no, we didn't put anything in, but we take large scale derivatives. So you can think that the memory comes from the spatial distances, right? In the sense that something that is there is going to influence you over here. And so that's a mapping, space and time mapping as being equivalent. So that's one way to think about it, but there are other ways to actually include memory. We've started a few things. I would say the jury is still out if it really matters or not. I think from a physics perspective, it does matter because nothing is really instantaneous. But in terms of results in quote, we haven't seen any major differences. But again, I would say the jury is still out because we probably are doing something wrong or the formulation of the problem is wrong. But yeah, great point.
Thanks. Are there any other, I see no other questions. Maybe now's a good time to end. I would like to remind everyone that our own Tiffany Shaw is giving the next APS GPC seminar on the 19th of October at this time. And once again, you can get it through the APS GPC webpage and get access to the Zoom link from there. So I want to thank everyone for attending and for these great questions. And I want to especially thank Laura for a fantastic talk. And Pedram's just dropped those seminar series links in the chat if you want to take a look. And otherwise, have a good rest of the day. Thank you.
Thanks, everybody.
Thank you, Laure.
Thanks a lot.